Hello, my name is Praveen. This is my video submission as part of probability homework 3. So in the first problem we are given the joint density function f of xy equal to 1 plus xy by a. X ranges from minus 1 to 1 and y goes from minus 1 to 1. So we are asked to find the constant a. By the property of a PDF, we know that a double integral minus infinity to infinity of both the integrals f of xy is equal to 1. So using that and evaluating the integral, we arrive at the answer of a equal to 4. So f of xy is 1 plus xy by 4. In the interval, x tends to minus 1 to 1 and y goes from minus 1 to 1. In subdivision 2, we are asked if x and y are uncorrelated. So the condition for uncorrelatedness is the covariance should be 0. That is, expectation of xy, joint expectation of xy should be equal to the product of the individual expectations. If so, they are uncorrelated. So the joint expectation of xy is nothing but evaluating the double integral for the corresponding limits of x and y. The integral to be evaluated is nothing but xy into f of xy dx dy. So using that, we get e of xy to be 1 by 9. Now to find expectation of x, it's the same formula except that in the integral we multiply f of xy with just x, and similarly for e of y we multiply the f of xy with just y and evaluate the double integral for both the cases. So we get e of xy to be 0. So now since e of xy, we got a positive value for e of xy, but e of x is just 0. So e of xy is not equal to e of x into e of y, so they are not uncorrelated. Since they are not uncorrelated, they are also not independent. In the fourth subdivision, we are asked to find the joint density function of x square and y square. So we take two random variables w and z and assign w to x square and z to y square to find the Jacobian. So the Jacobian consists of 4 partial derivatives, one with respect to x and one with respect to y, for both w and the z random variable. So we get the modulus of Jacobian to be 4xy. So since w equal to x square and z equal to y square, we get 2 roots for x and 2 roots for y. That is root of plus or minus root of w and plus or minus root of z. So totally there are 4 possible roots, namely root of z, root of w, and minus root of z, root of w, root of z, minus root of w, and minus root of z and minus root of w. So now the density function fzw is given by fxy at all the 4 roots divided by the Jacobian for I equal to 1, 2, 3, 4, since we have 4 roots. So evaluating this, we get f of zw as 1 by 4 root of z root of w. This can be split up as 1 by 2 root w, 1 by 2 root z. This is valid in the interval z from 0 to 1 and w from 0 to 1. So we can see clearly that f of zw equal to f of z into f of w, so they are independent, and since z and w are independent, x square and y square which we have assigned to them are also independent.